Hello students, welcome to our class, and this is Physics for Engineers. Lesson is about vectors. So by the end of this module, the student is expected to learn 1. Unit analysis, algebra, scientific notation, and right triangle trigonometry. 2. Scalar and vector quantities. 3. Components for a given vector. 4. Resultant of 2 or more vectors. And 5. Rectangular, polar, and vector notations. So first, let us discuss the unit analysis. I would not be discussing the those that have been discussed in the previous courses, like algebra and trigonometry. So let's go to the right to the things that we need in order for us to proceed smoothly with our lessons. So unit analysis is, in many situations, you may have to check a specific equation to see if it matches your expectations. A useful procedure for doing that, called the dimensional analysis, can be used because dimensions can be treated as algebraic quantities. Quantities can be added or subtracted only if they have the same dimensions. The terms on both sides of an equation must have the same dimensions. Suppose that you want to check the accuracy of the formula x is equal to 1/2 at squared. Later on, you will learn this formula, where x is the displacement and a is the acceleration and t is time. So x is equal to 1/2 at squared. Since displacement is expressed in meters in the metric system, we put m here. We put m here. Then 1/2 m over s squared, this is the unit for acceleration, meters per second squared, times second squared, which is the unit of time. So we have to square it also. We disregard the constant here because we only want the units. So as we can see, we can cancel out the second squared, and what remains will be the meters. So meters is equal to meters, and it follows the conditions stated here, in which quantities can be added, the terms on both sides of an equation must have the same dimensions. So with regards to scientific notations or scientific figures, you only have 3 rules to remember. So when you complete a result from several measured numbers, each of which has a certain accuracy, you should give the result with the correct number of significant figures. When multiplying several quantities, the number of significant figures in the final answer is the same as the number of significant figures in the quantity having the smallest number of significant figures. The same rule applies to division. When numbers are added or subtracted, the number of decimal places in the result should be equal to the smallest number of decimal places of any term in the sum or difference. Okay? And now we come to the main topic, which is vectors. So we have 2 types of quantities that we are going to deal with in this subject. So one is scalar and the other is vector. So a scalar quantity is completely specified by a single value with an appropriate unit and has no direction. Examples of scalar quantities are temperature, volume, mass, speed, time, and time intervals. Some scalars are always positive, such as mass and speed. Others, such as temperature, can either have positive or negative values. The rules of ordinary arithmetic are used to manipulate scalar quantities. Meanwhile, a vector quantity is completely specified by a number with an appropriate unit, or the magnitude of the vector plus the direction. Many physical concepts such as displacement, velocity, acceleration, force, and momentum are vector quantities. So suppose that we have a particle. So say this is particle A. It moves from this point to some point B along a straight path as shown. We represent we represent this displacement by drawing an arrow from A to B with the tip of the arrow pointing away from the starting point. So no matter even if the particle has to move in this along this path, which is obviously not a straight line, the displacement is still the shortest distance from the start position to the end position. So the direction of the arrowhead represents the direction of the displacement, and the length of the arrow represents the magnitude of the displacement. In our discussion, we will use the boldface letter with an arrow above the letter to represent a vector. Now, if you are writing on your paper and you want to use the vector notation, you can simply just write the uppercase of the letter, then put an arrow on top of it. So no need to make it boldface. So, but if you're going to write using your computer, please make it a boldface letter and with an arrow over the on the top of it. So the magnitude of the vector A is written as either the simple uppercase A or the vector notation A inside two straight brackets, which denotes that the absolute value of the vector is to be obtained. So the magnitude of a vector has physical units such as meters for displacement or meters per second for velocity. The magnitude of a vector is always a positive number. Vectors could either be expressed in a rectangular or polar notation. So rectangular notation is also called the unit vector notation, which will be discussed later, while polar notation includes the magnitude and the angle of the vector. So for the properties of vector, so the first property of vector that we are going to discuss is the equality of vectors. For many purposes, two vectors A and B may be defined to be equal if they have the same magnitude and if they point at the same direction. So in this figure, you can see that we have many vectors here, and I think they are the same length, and they point at the same direction, and they are inclined at the same angle with the x-axis. So even though these vectors are placed differently along the Cartesian coordinate plane, these vectors are all equal as long as they have the same magnitude and they point in the same direction, which means they have the same inclination from the xy plane. Now, for adding vectors, the rules for adding vectors are conveniently described by the graphical method. So, for example, I have a vector here, vector A. Then you have another vector B, and we want to add them together. We can just draw them like this with the first vector. Then we draw the second vector from the starting from the head of the first vector. Then to get the resultant, we draw a line, another vector from the tail of the first vector to the tip of the head of the second vector. So this vector R is the resultant of vectors A and B. So a geometric construction can also be used to add more than two vectors. So in our earlier example, we added two vectors, but you can also use the geometric method, the graphical method, to add more than two vectors. This technique for adding vectors is often called the head-to-tail method. So for example, we have the vector A here. We just draw the second vector from the head of the first vector. Then we do the same with the next vector. Then they do the same with the fourth vector. Then to find the resultant, we just draw a vector from the tail of the first vector to the head of the last vector. So this is the resultant vector. R is equal to A plus B plus C plus D. So please take note that even though the notation of for adding vectors is like this, it doesn't mean that we add the vectors algebraic like how we do algebraically. So it's not vectors don't work the same way as scalars, in which scalars can be added using the rules of arithmetic. So we are going to discuss that later on. When two vectors are added, the sum is independent of the order of the addition. So that means that if you add A to B, it's just the same as B to A. So A plus B is equal to B plus A. And that is called the commutative law of addition. When three or more vectors are added, their sum is independent of the way which the individual vectors are grouped together. And this is called the associative law of addition. So if you add first B and C, then you add A. It's just the same as adding A and B first, then adding C later on. So when two or more vectors are added together, they must all have the same units and they must all be the same type of quantity. So you cannot add velocity with acceleration, they're not the same. You cannot add temperature with distance. So that's our rule. They must have the same units and the same type of quantity. So the negative of vector is the vector having the same magnitude but opposite in direction. So I have a vector A here, it points to the right. So the negative of this vector is a vector of the same length but different has the different direction. So the tail of vector the head of vector A is here. While the head of negative vector A is on the opposite side. Okay. For subtracting vectors, the operation of vector subtraction makes use of the definition of the negative of a vector. So A minus B is equal to A plus negative B. That means that, example, I have here the vector A. So I want to subtract A and B. Vector A. So if we are going to add, suppose that we were to add A and B, then B will have to point here. It should have pointed here in this direction. But since we are subtracting the two, we reverse the direction of vector B like this and proceed to add the two. So connect the tail of A to the tip of B, and there we have the difference of vectors A and B. So another method of another approach for subtracting vectors is in this second figure. Vector C is equal to A minus B is the vector we must add to B to obtain A. So simple algebraic manipulation, we eliminate the negative here, and we can do that by transposing B to the other side of the equation. That gives us B plus C is equal to A. So in this example, in this approach, we want to find the vector that we must add to B to obtain A. Okay? So I hope that's clear. Now, to multiply a vector by a scalar, if vector A is multiplied by a positive scalar quantity m, the product MA is a vector that has the same direction as A and magnitude m times A. That is the magnitude m. M is the constant that we want to multiply. Then A is the magnitude of our vector. So if vector A is multiplied by a negative scalar quantity negative m, the product negative MA is directed opposite A. Okay? Okay, let us have an example. So in our example, we have Falco, the bird, flies 20 kilometers due north, then 35 kilometers 60 degrees west of north as shown. So we have here the bird falco, who is still a silhouette because he is still in the manga. Now he flies 20 kilometers north, then 35 kilometers 60 degrees west of north as shown, like that. So find the magnitude of this and displacement of Falco's resultant displacement. So we have to find the magnitude and direction. Sorry, this is direction. The direction of Falco's resultant displacement. So you have to know the magnitude and the angle. So recreating the problem here. So and plotting the positions of Falco in the coordinate plane. So we have 20 kilometers north going up the y-axis, then 60 degrees north west of north is at 35 kilometers 60 degrees west of north. That means from the north axis we are going to measure 60 degrees going west. So this is the 60 degrees. So we want to know the quantity, the magnitude of and direction of R. So for the magnitude, we can simply use the trigonometric laws here. We can specifically use cosine law because we have two sides, one side, two sides, and an included angle, which we can easily obtain if we are going to consider that this makes up a straight line, and the supplementary angle for 60 is 120. So that 180, this is 180 degrees minus 60 is equal to 120. So using the cosine law, r squared is equal to a squared plus b squared minus 2ab cosine alpha, in which alpha is 120. So r is equal to the square root of 20. This is 20, the green arrow, plus 35 squared, 20 squared plus 25 squared, the blue arrow, minus 2 times 20 times 35 cosine 120, and that gives us the resultant, which is 48.22 kilometers. So that is our magnitude. But since this is a vector, we need a direction, not only the magnitude but also the direction. So for the angle, we can easily obtain that using sine laws. So 120 can be paired with resultant r, then 35 can be paired with the angle here theta. So we can use any angle here, either the angle measured from the y-axis or the angle measured from the x-axis, as long as you specify from which axis are you measuring from. Okay, so 48.22, which is our resultant, over sine 120 is equal to 35 over sine theta. So our result is 38.95 degrees west of north. So that means that from the north axis, we are going to measure 38.95 degrees going west, okay, west of north. The graphical method of adding vectors is not recommended whenever high accuracy is required or in three-dimensional problems. Another method of adding vectors that makes use of projections of vectors along coordinate axis. These projections are called the components of the vector or its rectangular components. Any vector can be completely described by its components. So earlier, if you can notice, our sample problem about Falco the bird, we made use of polar coordinates of the polar notations to completely describe the resultant vector. So in that approach, we use the we obtain the magnitude and then the direction or the angle from the axis. But in this approach, we want to use the components of the vectors, or the rectangular components of the vector instead. We want to consider a vector A lying on the xy plane, so that will be our vector, making our arbitrary angle theta with the positive axis as shown. So I think I did not show the angle, but I think you can imagine it. The angle is measured from the positive x-axis. So this vector can be expressed by the sum of two other components, ax. So ax is the projection of the vector along the x-axis. Then it is parallel to the x-axis, and ay. So this is ay, which is parallel to the y-axis. In this figure, we can assume that ax, the magnitude ax, is a cosine beta, in which a is the magnitude of our vector a, ay is a sine theta, and a is equal to the sum of the squares of the x and y coordinates, x and y components of the vector, and theta is the inverse tangent of the quotient ay over ax. So in this figure, this is a guide for us to know what will be the sign, that should be given to the component of the vector that we are dealing with. So if ax points right and is positive, and ay points up and is positive, then your vector is at the first quadrant of the Cartesian plane. So it is pointing upward to the right. So if ax points left and ay and is negative, and ay points up and is positive, then it lies, and the vector is at the second quadrant of the Cartesian plane. So if ax points left and it is negative, and ay points down is negative, it is in the third quadrant. And if ax points right and is positive, and ay points down and is negative, then it is at the fourth quadrant of the Cartesian plane. Now we discuss the unit vectors. A unit vector is a dimensionless vector having a magnitude of exactly 1. Unit vectors are used to specify a given direction and have no other physical significance. We shall use the symbols I hat, j hat, and k hat to represent unit vectors pointing in the positive x, y, and z directions respectively. The hats, or the circumflexes, on the symbols are a standard notation for unit vectors, and the magnitude for each unit vector equals 1. Consider a vector A lying on the xy plane and making an arbitrary angle theta on a positive x-axis as shown. So that's our vector. The product of the component ax and the unit vector I is the component vector ax, shown in the figure. This is the component vector ax, which is equal to ax I with the caret, or I hat, which lies on the x-axis and has a magnitude ax. Likewise, the vector ay is equal to ay, so this is vector ay j hat, or j with the caret, which lies on the y-axis and has a magnitude ay. Therefore, the unit vector notation for vector A is vector A is equal to ax I with the caret plus ay j with the caret. So from now on, I will be pronouncing the I with the circumflex or caret as simply I, and j with the caret or j with the circumflex or j hat as simply j. So suppose we want to add vectors b and vector a using the unit vector notation. Because of the bookkeeping convenience of the unit vectors, all we do is add the x and y components separately. So the resultant vector r is equal to a plus b is simply r is equal to axi plus ayj plus bxi plus byj. So I think you already know where this is going. We just add the similar terms. Okay, so you just add the terms with I, then add the terms with j. So ax plus bxi plus ay plus byj, and there we have it. The resultant is equal to rxi plus ryj, in which rx is the horizontal component and ry is the vertical component. So the components of the resultant vector are rx is equal to ax plus bx, or the sum of the x components of the two vectors, and ry is equal to ay plus by. The magnitude of r and the angle it makes with the x-axis are obtained from its components using the relationships r is equal to r squared rx squared plus ry squared, which is equal to the square root of ax squared plus bx squared plus ax plus bx squared plus ay plus by squared. So this is how we convert the rectangular notation or the unit vector notation to polar notation. So the angle can be obtained from tangent theta, which is equal to ry over rx, which is equal to ay plus by over ax plus bx. For three-dimensional vectors, if a and b have both x, y, and z components, so we simply add the term azk, in which k is the unit vector for the z-axis. So b is equal to bxi plus byj plus bzk. So the resultant vector of the two vectors a and b is equal to ax plus bxy plus ay plus byj plus az plus bzk. Okay. As an example, we want to find the sum of two displacement vectors a and b lying on the xy plane given by a is equal to 2I plus 2j m is meters, and b is equal to 2I minus 4j meters. Okay? To draw the two vectors on the Cartesian plane so that we can conceptualize what's actually happening. So that is the first step on solving any problems. You conceptualize it, you draw it, you visualize it, so that you can truly understand what's happening. So in our Cartesian coordinate plane, this is vector A. So vector A is 2i plus 2j. So from the figure earlier, if I and j are both positive, x and y are both positive, then your vector is on the positive x-axis, positive x-axis, positive y-axis. Your vector is on quadrant 1. Now about vector B. So vector B has a negative y, so that means it lies here. It lies here on the fourth quadrant of your Cartesian plane. So resolving A into two components, x and y. So since this is already in rectangular notation, we can say that we can already take note that ax is equal to 2 and ay is also equal to 2. Okay? Now for the second vector, so this is your second vector. So the components are bx and by. So from the vector notation, you can already tell that the component of b, the x component of b is 2 and the y component of b is 4. So finding the resultant of the two, so the resultant of the two is just the sum of the x's then the y's. So 2 plus 2i plus 2 minus 4j, we have 4i minus 2j. Okay, so that will be our resultant. Now we want to know we also want to know the magnitude and direction of this vector r. So we can obtain that by converting this rectangular notation into polar notation. Okay, so to obtain the magnitude of r, we use this formula. R is equal to r squared minus 2 squared, simply x squared plus y squared, then take the square root of that, which is equal to 20, and which is also equal to 4.5 meters. Now for the direction of r, simply using the formula, that is tangent inverse negative 2 over 4. So we have negative 27 or 333 degrees. So negative 27 is also acceptable, but positive 333 is the angle measured from the positive x-axis counterclockwise. Going counterclockwise. Okay, so this is negative because the angle is measured clockwise. So if counterclockwise, it goes like this, from x to from the positive x-axis going to the left. So that will give us 333. So let's have another example. So this is Klee. Klee is merrily running around the fields of Mondstadt for 50 meters east when she sees Jean. So Jean is the guardian of Klee, and if she sees Klee running around, she might scold Klee. So Klee makes a sharp turn to 50 degrees north of west for 45 meters so that she could hide. Determine the components of Klee's displacement from her original position and express the resultant in terms of unit vectors. Okay? Example, this is Klee, and I have a compass here. So she runs 50 meters east. Then she sees Jean. She runs 45 meters to 50 degrees west of north. I think that's correct. West of 50 degrees north of west. Okay, 50 degrees north of west. So we want to know the resultant of the resultant displacement from her original position to her final position. So when we say 50 degrees north of west, so that is going from west north of west. So you take the last part of the direction first. From west, you measure 50 degrees going north. Okay? 50 degrees going north. So we have 50 here. Okay? Isolating our figure, or drawing a free body diagram like this, we have a triangle. So the unit vector notation for the first vector, which is A, is 50i, because we don't have a y coordinate for this because she is only going straight to the east, and no y coordinate is no y component is involved here, so we only have 50i. So the second vector, the unit vector notation for the second vector, that is when she made a sharp turn 50 degrees north of west, will be negative 45 cosine 50. So why negative? Because the vector is pointing to the left but upward. So technically, if you are going to draw this on the coordinate axis, this will be placed on the quadrant 2. So quadrant 2 has negative x but positive y. So negative 45 cosine 50, I hope you remember this formula, plus 45 sine 50 j. So we have negative 28.93i, so we can use the calculator to obtain this, plus 34.47j. So the resultant r is simply a plus b. So combine like terms, 50i minus 28.93i plus 34.47J, and that gives us the final answer 21.7I plus 34.47J. Okay, you can, as an exercise, you can try to obtain the magnitude of the resultant R and the angle from the positive x-axis. Okay, so that will be all for this lesson. I hope you enjoyed it, and see you next time.